Okay, 10(2) is about fractional exponents, and even though that we usually skip the section and call it optional, it's really important that we understand what fractional exponents are and how to rewrite them to understand how they're behaving. So recall an exponential expression. So we could have a to the m over n power if a is a real number, m is an integer, and n is positive. So if you have a negative exponent and it's a fraction, you let the negative go with the numerator, leave your denominator positive. And the nth root of a is a real number, then a to the m over n is the nth root of a to the m power, or the nth root of a to the m power. Now, all it's really saying is that if you've got 4 to the 5 halves power, this is either this 2 becomes the square root of 4 all to the 5th, or the square root of 4 to the 5th. Either one of those is the same. I recommend this one. It's easier to make your number get smaller by taking the square root before it gets bigger than to get a really big number and then have to try to figure out what the square root of that number is. So I would get smaller before bigger, so I'm going to always use this version. But generally, we need to be able to just rewrite these and then evaluate. So 125 to the 1/3 power. Again, this denominator, third power, means it is a cube root of 125. The numerator of 1 means raised to the first power, but anything raised to the first power is just itself. So this is just the cube root of 125. When you have a number raised to a fractional power where it's 1 over something, that's just the basic nth root, whatever that denominator is of that thing. Now the number times itself 3 times, that's 125, is 5. Negative 16 to the 3 halves power really means the square root of negative 16 raised to the 3rd. So this is why it's kind of important. What do we know about the square root of negative 16? Well, for now, we can't do anything with it. We'll learn how eventually. But we're not supposed to have negative under its square roots. So this has no solution. It's not possible. Generally, if you have a negative number and an even root, you can't do anything with it for now. 81 to the 7/4 power can be rewritten as the 4th root of 81 raised to the 7th. Okay, so this is a good example of why we don't use this method. Do you want to take 81 to the 7th power and then try to take a 4th root of it? Probably not. You'd be multiplying for a while. But the 4th root of 81 is 3. And 3 to the 7th power, if we count 3, 9, 27, 81, 243, so that's 5, 729, 2187. It would have been an insanely large number if we went the other way. Now, besides evaluating, let's just try writing in radical form. We should be able to do this if we've done the last thing. 4 to the 9/7 power is really the 7th root of 4 raised to the 9th. X plus 2y to the 7/3. Even though there's variables, we can still rewrite it. This is the 3rd root of x plus 2y, all raised to the 7th. Okay, so what happens if we have variables, and potentially how do we combine things? Okay, if we can go from rational exponents to roots, we should be able to go backwards to help ourselves. So when it says t to the 16th, the square root, this is really t to the 16th raised to the 1/2 power, going backwards. Then we can use our exponent rules to simplify. Power to a power, we multiply. So this is t to the 16 times 1/2. But 16 times 1/2 is 8. T to the 8th. The 5th root of x cubed times the square root of x. So now we've got more work to do. Again, this is x cubed to the 1/5 power times x to the 1/2 power. 3 times 1/5 is x to the 3/5 times x to the 1/2. If you multiply with the same base using our exponent rules, you add the exponents. 3/5 plus 1/2, which is 6/10 plus 5/10, which is x to the 11/10. Since it wants the answer written with rational exponents, we won't switch back to roots. The 6th root of y to the 5th over the 8th root of y cubed can be written as y to the 5th to the 1/6 over y cubed to the 1/8, which is y to the 5/6 over y to the 3/8. Now remember, if we're dividing with the same base, we subtract. So this is y to the 5/6 minus 3/8. Our common denominator between these two is 24. Y to the 20/24 minus y 9/24, which is y to the 11/24 power. And again, there's just more. Simplify the following. A to the 5/9 times a to the negative 1/7. Again, multiplying with the same base. You add exponents. Common denominator here is 63, 9 times 7. So I need to multiply my first fraction by 7. That's 35 over 63. Plus a negative 1/7 is the same as minus. If we multiply by 9, this is 9 over 63. So in total, this is a to the 26 over 63rd power. X to the 3/5 cubed over x squared to the 7/5. 3/5 times 3 is 9/5. 2 times 7/5 is 14/5. Dividing with the same base, we have 9/5 minus 14/5. Already has the same denominator, so this is x to the negative 5/5, but that reduces to x to the negative 1st power. Now we know from our exponent rule section, we can take negative exponents and flip them. So this is 1 over x to the positive 1st, or 1 over x. And lastly, the 7th root of the 4th root of z to the 3rd. So let's work on just the inside of the 7th root first. This is the 7th root of z to the 3rd to the 1/4 power, because it's a root. So that's the 7th root of z to the 3/4. Now the 7th root is also a fractional exponent, so we've got z to the 3/4. This becomes times 1/7. And again, we multiply powers. This is z to the 3/28 power. And that's really all for this section. It's mostly about you getting familiar with those rational exponents and what they look like. This is extremely valuable in the first week in college algebra when we get there, so I still recommend you be aware of what these look like.